on this video lecture of SC Electronics class self Patil, Department of Electronic Science, College Nas. In this video, we shall learn incompletely specified state table and finding the equivalent state that incompletely state table. So let us start. First of all, we'll see what is meant by incompletely specified state table. In the combinational logic circuit, face the conditions where truth table is not completely specified, and in such a case we write it as a don't care terms. The same thing is there in the sequential circuit if either state transitions or output variables are not completely specified. When state transitions are not specified, the machine is not predictable. We cannot predict the behavior of that machine under such a conditions. It is expected to avoid such situations either by specifying input sequences so that no next state is unspecified, or by assigning the next states that are not contrary to the desired result. When next states are assigned to cover those initially unspecified conditions, the state, the machine is no longer incompletely specified. The unspecified outputs can be assigned without any impact on the state sequence or the final state table. The outputs are unspecified, they are to be specified in such a way so that there will be no impact on the state sequence of the final state machine, and that must be taken care. It is always advantageous to leave don't care outputs unspecified as long as possible during the state reduction process. This provides additional flexibility in reducing the state table. The two states are equivalent, they satisfy the property of equivalent states. This requires that output to be the same for equivalency to exist, that we know. The state compatibility term is used of equivalence when reducing incompletely specified state table. That is important. The state compatibility term has to be used instead of state equivalency, reducing incompletely specified state table. So first of all, the definition of compatibility is given. The two states A and SB are compatible states if for every input sequence that affects the two states, the same output sequence occurs. When the incompletely specified states are specified, regardless of whether SA or SB is the starting state. So, in the compatibility, we can say the two states are compatible if their output is same. The same output sequence occurs when states are incompletely which were incompletely specified, they are specified, and it is material is the starting state, their first state or second state, say or SB, that is immaterial material in that case. Let us see the example of incompletely specified state table. A state machine is described in state table where it contains the 5 states starting from S0, S1, S3, S4, and the next state and output columns are given. The next states are given while some of the output states, column, 4 state, 4 output conditions are missing out there. Similarly here, one output state is missing. So such a state table is called incompletely specified state table. And in such a situation, as described earlier, solving such a completely specified state table or finding your compatible states completely simple, we have to use implication chart method where we fill the implication chart as per our usual method, and unspecified output will be tried kept unspecified as long as possible. So let us see how it is to be done. See here, the state table is taken and the implication chart has to be filled. So as we know how to draw the implication chart, the five states starting from S0 to S4 along the column, we take all the state except the first one, that is S0 is missing, while all rest of the states are taken along the row. Take the first four state while the S4 fifth state is missing, and accordingly the prepare the squares, and then as initially we take care of outputs and accordingly place the cross mark in the respective square where the outputs are different. So first of all we'll check the outputs for state S0 and S1, the first square here S0 S1. Check the output 0 and unspecified. Unspecified state or the output is like a don't care condition in the state table or the truth table, so we can specify it either 0 or 1 as per our convenience. So here we can specify 0. Therefore we can say the S0 can be compatible to S1. The outputs are same, output here can be same, and next state or the potentially implied state by which they can be compatible is S0 S0 same state, always compatible S1 S2. So S1 S2 state pair is written. The next S0 S2, check the output first. 0 unspecified, it can be 0. Here 0 and 1, the output is different, so we'll place the cross mark in S0 and S2. So S0 and S2, this square the cross mark is placed. Then check the next is S0 and S3, output 0 unspecified can be same, 0 0 it can be same. Now place the potentially compatible state pair by which they can be compatible. It is S0 S4 and S1 S2. So these two state pairs are placed in the S0 SD square. The next is S0 S4. Check the output 0 unspecified can be same, 0 unspecified same. So S0 can be compatible to S4 by the potentially compatible pair. S0 S0 it is same, but no, there is no need to write those state S0 and S1 because S0 is compatible to itself and S1 is compatible itself. Okay. The next is S1 and S2. Check the output. They are the same, but here 0 and 1 it is different, so place the cross. The next is S1 S3. Check the output. Unspecified, unspecified, so 0. So they can be compatible. The compatible state pair, potentially compatible state pair are S0 S4 and S2. So we'll write S0 S4. 2 is need not to be written. The same state are compatible that we know. The next square is 1 S4. Check the output as unspecified, unspecified. It can be same and 0 and unspecified. 0 here, so it can be compatible. And the potentially compatible pair, that square is S0 S0 and 1 S2. 1 S2 is the next square is S2 S3. Check the output specified unspecified here 1 0. So they cannot be compatible. So X cross mark is placed here. S2 S4 S2 S4, check the output conditions. Unspecified can be here, one specified can be compatible. And the potentially compatible state pair in that square is S0, S3 and S1, S3. S0, S3 and the last is S3, S4. The output can be here, it can be same, and here we can specify 0. So output can be same. And the states by which they can be compatible is S0, S4 and S1, S2 and S1, S2. Okay. So in this way, all the squares are to be filled either potentially compatible state pair, and in the square where outputs are different we place cross mark like this. Now check the potential compatibility of the squares where state pairs are written. Now here S1, S2 is get crossed, S0, S2 is get crossed, and S2, S3 is crossed in the square where such that these pairs are present. All of them will get crossed. First here see S1, S1, S2, S0, S1 square contains the S1, S2. Since S1, S2 is get crossed, square will then this one will also get this will also get crossed. What is left? This one S0, S3, 0, S3. Check the compatibility of S0, S3. It is also get crossed in its square, so also get the uncrossed squares are S0 and S4, and here is here it is compatible, and in this square it is compatible by S0 and S4. So we can say S0 is compatible to S4 and S1 is compatible to S3. Okay, so here we have to specify S0 is compatible to S4, 0 is compatible to S4 when in the input under input condition x equals to 1, output z is specified as 0, so 0 must be placed there, and under input condition x equals to 0, the output z is specified as 0. Okay, similarly S1 is compatible to S3, S1 is compatible to S3 under input x is equals to 0, output z is specified as either 0 0 or 1 1. So all the zeros there, and in this way we have kept unspecified outputs unspecified as long as possible, and once they are specified get the function that table. So in this case S0 is compatible to S4 and S3 are the compatible state pair. The explanation of that state table and application chart is described here. S0 is compatible to S4 if Z or S4 when x is equals to x is 1 is changed from 0, that is written here, or under input x is equals to 0, output z is changed from 0, or x is equal to 1, output z is equal unspecified 0. Okay. The next is S1 is compatible to S3, output z for S1 and S3 x is equal to 0, change from don't care to either 0 1, but both need to be same. In this case we have assigned 0. By that way it can be compatible. Therefore we assign z equals to 0 for present 4 when x 1. The other don't cares are out, so don't care outputs are left down to use multiplication. We have just specified it as a 0 in our example. Once we find the compatible states, we can modify the state table, we can simplify the state table, name the state table states. Here S0 is renamed as A, S1 is renamed as B, Is once it is done, you can get the modified state table. In this, the two state S4 and S3 get eliminated from the original states are left there. They are renamed as AB. They are prepared, the simplified state prepared. In this state table, it contains only three state, while the earlier one was containing the five state. And to implement the state machine with five state variables, we require five states. We require three state variable, while the state machine containing three state, it requires only two state variables or two flip flops. So one flip flop is get reduced, and by that way, we can reduce the circuit cost, circuit complexity, and enhance the speed. So these are the advantages of reducing the number of states, sequential state machine. So with this conclude. Thank you very much. Thanks.